Bismillahirrahmanirrahim. Assalamu alaikum, dear students. We are now starting the third lecture for our week number 6 of the course Communication Systems. In our last week's discussion, in the discussion, in the last lecture's discussion, we talked about the spectrum of FM and PM signals. So we have discussed that the spectrum of PM and FM signals is rather complicated as compared to the AM spectrum, and for the case of tone modulation we derived some results based on the Bessel function. So as I previously mentioned in my last lecture that the exact analytical results for the spectrum are really hard to obtain, but from the tone modulation results that we discussed in our last lecture, we can easily draw conclusions regarding the bandwidth of FM signal. In today's lecture, we'll be talking about the bandwidth of FM signal. If you recall, in the previous analysis, we discussed that the theoretically FM signal requires infinite bandwidth because there were infinite number of terms in the expansion of the spectrum in form of the Bessel function. So being infinite number of term, when you plot it, you would have an infinite spectrum. However, practically it is not possible. We should have a finite bandwidth, and we need to restrict bandwidth at certain range. So how can we do that? In order to restrict the bandwidth of FM signal, we need to have an appropriate criteria, and the criteria should be such that there is the restriction of bandwidth does not create any significant distortion in the signal. So we should have a certain criteria so that we can limit the bandwidth without causing distortion to the signal. In order to do that, we need to restrict the number of spectral lines, because initially, as we discussed in our last week lecture, there would be infinite number of spectral lines, and in order to restrict the bandwidth, we need to restrict the number of spectral lines. And in order to do that, we need to determine which spectral lines they are significant. So we need to understand how much spectral lines are significant. In order to do that, you should realize that Bessel function reduces very fast when the n becomes greater than beta. So for large value of n, the Bessel function it reduces very fast, and therefore the significant spectral lines will be the one for which the value of n is small. So in other words, we can say that the most significant spectral lines will be the one where this n is smaller than beta, or beta was defined as am f delta upon fm, like this. So we get a simple mathematical condition that in order to have a finite bandwidth, the significant spectral line that should be included should satisfy this condition that n should be smaller than beta. And from here, the number of spectral lines that will be the frequency band that will be placed in the FM signal with respect to this criteria would be restricted by this value fc plus minus beta fm. So the bandwidth will be starting from fc minus beta fm and would end at fc plus beta fm. However, this is not a very good criteria. Actually, practically we need to take some additional lines as well, because with this criteria we have some distortion in the signals which cannot be tolerated. So what is the better criteria? In order to understand that, we should see this thing. So because the Bessel function, we need to determine which Bessel functions they are significant. So we have chosen a specific value epsilon, and if the Bessel function value is greater than epsilon, we'll treat it as significant. Practically, we take epsilon to be in between the range of 0.01 to 0.1, that is from 1% to 10%. So these two lines here, they corresponds to two different values of epsilon 0.01 and 0.1. So we determine all those lines which are significant and satisfy this criteria. So all the lines will be included here. So if there is only one line, so that means there will be one sideband. If there are two significant lines, that means there will be two sidebands, and so on. If you recall, in AM signal, we talked about a single sideband because there is one sideband which was upper sideband, and there was one sideband which is lower sideband. So at one side there is one significant sideband, and for that you need to have the bandwidth of 2 FM. So that was the bandwidth with one sideband, and for this case we are talking about a number of sidebands. So that number of sidebands is denoted by m beta, number m. So in order to get the overall bandwidth, we need to multiply this 2 FM with m beta. So this m shows the number of significant sidebands, and 2 FM is the message bandwidth. So from this criteria, we typically determine how many sidebands are significant, and then by using this formula we can calculate the bandwidth of FM signal. However, there are certain other approximations that are also used commonly. For example, when beta is greater than 2, this m can be easily approximated as beta plus 2. You can see this dotted line here which shows the beta plus 2 line, which is a good compromise between these two criteria, 0.01 and 0.1. So this is practically acceptable result. In most cases we can use we can approximate number of sidebands to be equal to beta plus 2 for the case when beta is greater than 2. So the bottom line is, in order to do that, we need to determine the number of significant sidebands which should be included in the system, and for that case a simple table has been prepared. It's included in the book. It's table 5.1-2 with a criteria of 1%, that is epsilon is taken as 0.01. So this table shows the number of sidebands. You can see that when beta is 0.1, there is only one significant sideband. With the beta is equal to 0.5, you can see there are two sidebands. The first one will be the carrier, and the other two would be sidebands. For beta is equal to 1, you can see that there are three significant sidebands, and so on. So you can see that this table shows the significant sidebands and their corresponding amplitudes to represent the bandwidth of the FM signals. So from this table we can conveniently determine the bandwidth of the FM signal. Let us take a very simple example in order to illustrate how we can use this table to determine the bandwidth of FM signal. So let's say we have the modulating frequency, which is 3 kilohertz, and the maximum deviation, which is given as 6 kilohertz, and we want to find modulation index as well as the bandwidth of the FM signal. The modulation index, we know that it is defined as AM f delta upon FM. Of course, in most cases we take AM to be equal to 1. It's not mentioned in the problem as well, so it is convenient to take AM to be equal to 1 because we generally work on the normalized signals. F delta, the deviation is given as 6 kilohertz, and the modulating frequency is given as maximum modulating frequency is given as 3 kilohertz. So this beta comes out to be 2. Now the next task is to determine how many sidebands would be significant, because once we know the number of sidebands which are significant in calculation of bandwidth, we can easily calculate the bandwidth by this formula. Bandwidth should be equal to 2 FM multiplied by this number of significant side bands. So you can so for beta is equal to 2, we should refer to the table here. You can see that this table plots different values of beta starting from 0.1, 0.2 and up to 10. So beta is equal to 2 is this part, and you can see that this is the basic carrier amplitude, and there are 4 side bands shown here. So there are 4 side bands which have the amplitude more than 1%, that is 0.01. So in our case there are 4 significant side bands. Therefore the bandwidth would be 2 multiplied by 3 kilohertz multiplied by this 4, which shows the number of significant side bands. So it comes out to be 24 kilohertz. At this stage I would like to mention one more thing as well, because previously we have discussed the narrowband FM and we use the condition that beta should be smaller than 1. However, from this description we can easily see that beta can have even larger value, and for this case where the beta have the value which is which corresponds to only one significant sideband. So typically in FM systems we generally take the FM to be narrow band if the FM system has the modulating index which is less than this value pi by 2, 1.57. So for practical consideration we generally use this condition that beta the narrowband FM should have this beta value which is less than 1.57. Okay, in analysis normally we use another term which is named as deviation ratio instead of modulation index beta. So FM signals they are normally represented in terms of their deviation ratio. Actually the deviation ratio is defined as this f delta upon w, where f delta is the maximum deviation and w is the bandwidth of the message signal. You can see that this comes with direct analogy here, where FM is replaced by the W and AM is taken as equal to 1. So this term becomes the deviation ratio. So consequently we can conveniently show the bandwidth to be equal to 2 into this M, which shows the number of significant side bands, multiplied by W. So 2W is multiplied by the number of significant side bands, and this M can be determined from the table as we previously discussed, but there are certain approximations that we commonly used in practical implementation of system. So the common operating region for FM is generally taken as D between 2 to 10. So for this case, this number of sidebands can be conveniently approximated to be D plus 2. And if we use this relationship here, MD is replaced by D plus 2, we get a simple relationship that the bandwidth can be approximated as 2D plus 2W. And if you substitute the value of D in this relationship, we can get the bandwidth to be equal to 2FW F delta plus 2W. So this is a commonly used relationship. In some other applications there is normally another rule which is commonly used, which is called the Carson's rule. So Carson rules is actually a conservative approach in calculating the bandwidth of FM signal. In Carson's rule, this MD is generally approximated as D plus 1 rather than D plus 2. So if we approximate this number of sidebands, significant sideband, as D plus 1, so the bandwidth would be given as 2D plus 1 into W, or the bandwidth would be given as 2F delta plus W. you should notice that if f delta is much greater than w, like from this relationship, in that case this w would become insignificant and the bandwidth would be approximated as 2 f delta. So these are the mathematical approximations that are commonly used to determine the bandwidth of the message signal. Let us take another simple example. In most broadcast systems, f delta is generally taken as 75 kilohertz and w is generally taken as 15 kilohertz. In that case, the deviation ratio is 75 divided by 15, which is equal to 5. If we calculate the bandwidth with this relationship, which actually relates with the low distortion in the FM signal, so if we use this low distortion criteria, so bandwidth would be approximated as 2 into 5 plus 2 into 15 kilohertz, which comes out to be 210 kilohertz. If we try to approximate the bandwidth by using this Carson's rule, you can see that the bandwidth can be approximated by this relationship, which comes out to be 180 kilohertz. However, for tone modulation case, we can see that the FM is 15 kilohertz and AM, of course, we will be taking as 1, beta is 5, and for beta 5, how many sidebands are significant? You can see that for beta is equal to 5, you would be having one center frequency and then 7 significant sidebands. So there would be 7 significant sidebands here. In that case, if you determine the bandwidth, it will come out to be 210 kilohertz. However, we know that the audio frequencies, the voice, if we talk about only voice signal, that voice signal only has the maximum frequency which can be approximated as 3 kilohertz or 3.3 kilohertz actually. So in that case, beta would come out to be 25 and the number of significant sideband would be 127 and bandwidth comes out to be 162 kilohertz. So you can see that there are number of ways in determining the bandwidth of the FM signal which are practically used. So if we are interested in having very low distortion, in that case this criteria, the low distortion criteria gives you a better result. However, if you are more concerned about the bandwidth, in that case generally we use Carson's rule, which is given by this relationship here, and we use this Carson's rule to determine the bandwidth. Similar to the FM signals, the bandwidth of PM signals can also be calculated. However, in that case, the bandwidth would be dependent on this phi delta, which is actually the deviation, phase deviation, and we calculate the number of significant sidebands. However, we know that phi delta cannot be a large number because we have the restriction that phi delta should be smaller than pi radians. So therefore, we generally refer to it as narrowband signals, and we do not count it as very wideband signals because they have relatively smaller bandwidth. And in that case, we can simply approximate this bandwidth to be equal to 2 phi delta plus 1 into w. So this gives you a conservative approach related to calculating the bandwidth of the PM signal. So these are the relationships that we use to determine the bandwidth of FM and PM signals. With this, we conclude our discussion related to the bandwidth of the FM and PM signal. There are few minor topics related to the FM signal, so let us quickly discuss those things related to FM signal. There is a one good property of FM that I also discussed at the introductory lecture in FM, that it has a good noise suppression characteristics. So the noise has typically has low impact on FM signal as compared to the AM signal. Why it has low impact? Actually, noise, as we know that noise can come from the number of sources. Typically, that noise appears as narrow spikes of voltage at relatively high frequencies. So these narrow spikes, they generally add up to the signal, and of course that interfere with it. So you get a different you get multiple noise spikes in the signal. Sometimes if this noise is very high, they can obliterate the signal information as well. However, for FM signal, we know that there is a very good property of FM signal, that it has a constant amplitude of the modulated carrier. So amplitude does not change in FM signal. Rather, the information is contained in the frequency of the signal. So once these spikes, the noise spikes, they are added to the signal, they are actually changing the amplitudes. And therefore, typically what we do, we use a limiter circuit in the receiver side. That limiter circuit actually limits the noise spikes in the receiver and eventually removes the noise component from the receiver. And you can see from this diagram here, so if this red line represents the FM signal, and these black lines here, they are representing the spikes added because of the noise. So you can see that this is an FM signal which is coming with noise. So once we pass it through a clipper circuit, so clipper circuit clips this amplitude from to a certain voltage limit depending on the amplitude of the carrier. So you can see that as it limits the amplitude, so the noise spikes which have the amplitude beyond this limit, all these spikes, they will be removed. Although still there will be a small amount of noise which would be this part of the signal, this lower part, but still significant energy from the noise would be easily removed by simply passing this FM signal from a clipping circuit. So these clipping circuits, they can be easily used to remove the noise, and they do not affect the information contents in the signal. Why they do not affect the information contents? Because the information is not contained in the amplitude. So clipping the amplitude does not change the information because it's not in the amplitude. Rather, the information is solely contained in the frequency variations. So we can conveniently use this clipping circuit to remove the component of the noise. There is another technique to reduce the noise in the FM signal. Actually, the noise in FM signal can be further reduced by a technique which is called preemphasis and deemphasis. What happens in signals? Typically, these noise spikes, they have a larger effect at high frequencies. So generally, we see these spikes at relatively high frequencies. So high frequency components, they are more susceptible to the noise. You should recall that the parameter that we are interested in at the receiver is signal to noise ratio, or SNR, signal to noise ratio. So we are interested in having high signal power with respect to the noise power. So if we supply the same amount of power to the low frequency components and high frequency components, so eventually those high frequency components would get a larger amount of noise, and eventually the overall signal to noise ratio would be degraded. So how can we improve this signal to noise ratio? We can selectively amplify the components which have high frequency. That means we can have a circuit in which the high frequency components, they have a larger power as compared to the smaller power. This technique is called preemphasis. In preemphasis, we provide larger amount of power to the high frequency component, and we do not provide any extra amount of power to the low frequency component. Practically, a simple high pass filter can be used as a pre-emphasis circuit. So actually this pre-emphasis provide more amplification to high frequency components. So this is an illustration of pre-emphasis circuit. This part is a high pass filter which works as a pre-emphasis circuit, and then we frequency modulate the signal and we transmit it to the receiver side. At the receiver side, we use a de-emphasis in order to cancel the effect which was created in the pre-emphasis phase. So we try to selectively balance the effect of the circuit of the pre-emphasis. That is, we try to reduce the extra amount of power in the high frequency component, and when we try to reduce that amount of power in the high frequency component, eventually it also reduces the power in the noise as well. So although the signal power is reducing, but the noise power also reduces. Eventually the overall signal to noise ratio, it gets increased. So practically a simple low pass filter is used as a de-emphasis circuit in the receiver, and it is designed in such a way that it balances the changes made at the pre-emphasis phase, so that you get an overall flat response. So the combined effect of the pre-emphasis and de-emphasis is to increase the overall signal to noise ratio. In other words, the overall effect of this pre-emphasis and de-emphasis is that the overall noise in the system gets reduced. This is an illustration of de-emphasis circuit. So you have a FM signal coming in. First we demodulate it, and then we pass it through a de-emphasis circuit, which is actually a low pass filter, and whose frequency is chosen in whose cutoff frequency is chosen in such a way that it actually balances the response which was generated by this pre-emphasis circuit. So with this application of the pre-emphasis and de-emphasis in the FM signal, we get further improvement in the noise. So summarizing the discussion, what we see that the FM modulation, it has a very good property of noise suppression, because the information contents which are changed by the signals which are changed by the noise, they can be easily removed by limiting the variation in the FM signal by passing through a limiting circuit. So those noise spikes can be removed. Further, we can use pre-emphasis and de-emphasis to selectively amplify the high frequency components, and then de-amplify at the receiver side in such a way that the overall signal to noise ratio gets improved. So with this, we conclude the discussion on the FM modulation, and at the end we make a simple comparison of frequency modulation and the amplitude modulation that we have previously discussed. So there are certain advantages of using FM that we have discussed previously. First of all, the FM modulator, it has superior immunity to noise as compared to the AM signal, because we can use simple clipper limiter circuits in the receiver to remove the contribution of the noise, or at least reduce the contribution of the noise. There is another good property of the FM signal which is named as capture effect. Actually, when there are multiple transmissions in the region, we know that those transmissions, they can interfere with each other, but in FM the interfering signals which are at same frequency, they are rejected, so they do not contribute to the overall interference. So eventually this FM also provides a better immunity to the interference as well. Another advantage of using FM signal from the practical perspective is that because we are working on a constant amplitude, so we do not need to use a linear amplifiers to increase the power level. We are not required to use those linear amplifiers. This will improve the overall transmitter efficiency. That means you can make the transmission at even smaller amount of power. We realize that there are certain advantages of FM, but there are certain disadvantages as well. And one of the biggest disadvantage that we have previously discussed is that it requires more space, more bandwidth. So FM uses considerably large frequency spectrum, whereas the AM signal can be transmitted by using a smaller spectrum or smaller bandwidth. So FM signal require larger bandwidth. That means in a certain environment we can only accommodate a smaller number of FM signal as compared to the AM signal. Second problem related to the FM signal is that the circuitry which is used for FM modulation and demodulation is rather complex as compared to the AM signal. However, with the advancements in integrated circuit technology, the complex FM circuitry has been replaced by these integrated circuits, and we know that these ICs, they are relatively inexpensive and easy to use, and because of the availability of good ICs that can be used for FM modulation and demodulation, in many practical systems we are now using FM modulation techniques more widely as compared to the AM modulation. So with this we would conclude today's discussion. For today's discussion we have talked about the bandwidth of the FM signal and how the bandwidth can be approximated for practical purposes. Secondly, we have also talked about a very good property of FM systems, which is the noise suppression capability of FM signal. And third, we tried to make a simple comparison in terms of advantages and disadvantages between FM and AM signal. So this concludes our discussion for this lecture. So I would take the leave. Thank you all.